Hi, in this video we will learn about projection of a vector over another vector. What is the setting? The setting is that we have two vectors, u and v. We want to find the perpendicular shadow of v over u, or the projection of v over u, such that this line of the edge of the shadow is perpendicular to the vector u. So in other words, we are interested in this vector here, p. It is a vector you get from v and u, and we will call that vector projection of v over u. Well, we will find a formula for that, and then when we set up the formula, I will tell you what is the better notation for that. So let us start with some points or some remarks on this thing. First of all, the vector p is going to be parallel to u. So that's the first point we have to notice. P is parallel to u. Well, why? Because the projection is on u, but you may say that actually p and u are going to have same direction, because, well, you see that this is u, and then this is v, and when you project on this, you basically get a vector in the same direction. Yes, but you have to be careful. There is another case in which the vector v and u, the angle between the v and u is not a acute angle. In that case, when you're trying to find the perpendicular shadow, f won't sit on the same direction as u. It will be on the opposite direction of u. So let me just put the names over there. So that means that, well, these two are going to be just parallel, not same direction. And being parallel tells us what? Tells us that we can find a constant c such that when you multiply to u, you get the vector p. That's the meaning of parallel for some scalar c. So that is a good setup for now, at least. Now we know that it will be a multiple of u, and we have to find that multiple. What is that number? But we can go a little bit further in this, and I will write as the second point or second remark, that length of p, length of p or even p itself is independent of the length of u. Why? See, this is the vector u, this is the vector v, and when you find the shadow, you find this thing, vector p. Now let u be longer. Well, the shadow doesn't change. Let u be shorter. Well, the shadow doesn't change. Even if it is like that, doesn't change. It will just go. What matters is not the length of u. Well, vectors have two things. If it doesn't depend on the length, it will depend on the direction. So P depends on the direction. Actually, we can see that P is multiple of normalized, the direction of U is what? The normalized U, so this guy. Yes, so it means that not only it is C times U, but also it is multiple of 1 over length of U times U, and that multiple, this time I will put a tilde over that, meaning that it's not the same C as before, but it's a scalar for some scalar, C tilde. That's the second thing. The third thing is that though the length of the vector U doesn't change vector P, but the angle between U and V, it really changes P. So in other words, angle between V and U plays an important role. Why? Well, look at this examples here. So I have U, then V is this. I switch it to this one, same length but different angles. Switch it this one, switch it this one. Each one, only the angle changes. Here for this one we will get this projection. For this other one we'll get this projection. For this one we'll get 0 projection. For this one we'll get this projection. So the angle is going to play a very important role. But the role of the angle, we can quantify it. How does that play a role? Well, see, this is if theta is acute angle, then we have what? This is vector V, then this is vector P, and we know that this is perpendicular. Well, then we have right angle, and this is the same angle between U and V. Well, then we can define the vector, the definition of cosine theta. It means that, well, cosine theta is length of adjacent to hypotenuse. In other words, the length of P is length of V cosine theta. Well, what else we know? We know that this is also true. So let me combine this with that. We know that P is of the form C tilde 1 over U, length of U times U. And then property of length says that this will, the absolute value of C will come out, and then we will have length of U over length of U. So this is a unit vector, so that means that we have absolute value of C tilde times 1. And that's absolute value of C tilde. So the absolute value of C tilde is going to be length of this, and we know that length is a P. So C, absolute value of C tilde is length of V times cosine theta. We almost found everything. At least when theta is acute, in other words, between 0 and pi over 2, then the C is going to be positive. C tilde is going to be positive because P is going to be in the same direction as U. So then P is going to be exactly length of V cosine theta times 1 over U, length of U times U. Well, we have a formula for cosine theta in terms of U and V. Then times 1 over length of U times U. See that this, oh, not that one, sorry. This cancels with that, and then what we get is U dot V over length of U times itself, which is squared, times the vector U. So this is a constant multiplied to U. In other words, this is the scalar C that we found in part. We said there exists in part 1. But we can do a little bit more, that this is U dot V over length of U squared is U dot U, and that is, and well, this gives us a nice formula. If you give me what is V, what is U, I can find dot product of UV, dot product of U by itself, and then divide them, get a number, scalar multiplied to U. But you may say that, what about if theta is not acute? So what about the case that theta is between pi and pi over 2? In that case, what will happen is that cosine of theta is going to be negative, and C tilde is going to be also a negative number. So both being negative will still give us, the similar computation will give us that C tilde itself is length of V times cosine theta. In other words, the negative number, negative sign of C tilde will come from cosine itself, so we don't need to be worried about that. And then similar for computations will give us the same formula. Wrap up, here is that projection of vector V over U is denoted by, so we need to choose a nice notation. So projection of V over U is given by, I don't need to put is there, then it's given by the formula. Projection of V over U is U dot V over U dot U times U. Again, this part is a number times scalar, no, times U. That is the formula we need to know, and that's what we will use for projection.